Hello, everyone. In today's lecture, we will be talking about the difference between population means, where the two samples are independent. So now here we will see how to perform a hypothesis test and construct a confidence interval for the difference between the population means of two independent samples. So when we do inference, always what we try to do is that we need to figure out the distribution of the statistic. In this case, our statistic is okay. So the statistic is the difference between the two sample means, x bar 1 and x bar 2. So because what we're trying to estimate is this one, the difference between the two population means. And the estimate of this one is the difference of the sample means. Therefore, what we need to do is, or what we have to figure out before we go to the procedure is, we need to figure out the distribution of this one under some, of course, under some assumptions. Therefore, let me go a bit up. So here, the mean, well, this is the statistic. And if you remember, let me remind you this. For a single sample, the mean of x bar, if you will remember, it was mu, the population mean. And the standard deviation of x bar, or the standard deviation of x bar, was the standard deviation of the population divided by the square root of n. Okay, so these were for a single sample, for a single population. And now for the difference of two sample means, the mean is given by, let me write down here, mu x bar 1 minus x bar 2, these are sub-indices, is just the difference between mu1 and mu2. Okay, so the mean of the difference is the difference between the two means. And how about the standard deviation of this statistic? This is the statistic that we are trying to figure out its distribution. And the standard deviation of this, x bar 1 minus x bar 2, is sigma 1 square. Well, this is the variance, or we can say the standard deviation, it doesn't matter. I can write it in standard deviation. So this, oops. The standard deviation of the difference between the two samples is given by sigma 1 over n1 over root n1 plus sigma 2 over root n2. Sorry, this has to be n2 and this has to be n1, where the sub-indices 1 represents the sample 1 and sub-indices 2 represents sample 2. This one, don't get confused with this. They are basically the same. This is the standard, the variance. If you notice here, we have the square, both of them. Now, if you take the square root of this on both sides, what you get is that exactly this one. On the left side, you will have sigma x bar 1 minus x bar 2. You will take this one out of the square root. And here, sorry, here I did a mistake. This has to be overall sigma 1 square over n1, yeah, because there is a summation and I was not supposed to take it out. Mathematical, that's wrong. All right, so this is the standard deviation, yeah. And yeah, exactly, we have it here. All right, so now we know the mean of the statistic and the standard deviation of the statistic. Well, that's not enough. I know the mean and I know the standard deviation of the statistic, but I need the distribution. Now, under some assumptions, when some assumptions are met, this x bar 1 minus x bar 2 is approximately normally distributed. Now, what are those assumptions? One possibility is when n1 and n2, both of them are large. Remember, large means both of them have to be greater than 30, greater or equal to 30. So this is one possibility. If we have this condition, or if this condition is satisfied, then we can say approximately the distribution of x bar minus x bar 1 minus x bar 2, the distribution of this guy is approximately normal, with mean, as we mentioned here, with this mean and with this standard deviation. And another possibility, let's say this large sample criteria, we don't have it, or it's not met. Then another possibility that we need to look at is if the population distribution are approximately normal. Now, when we select the two samples, here is population 1, here is population 2. Now from this one, we will get sample 1, smaller. And from this guy, we will get sample 2. This is 1, this is 2. So one possibility is N1 and N2. By looking at this two, if they are large, then we can say approximately this follows normal distribution. And the other one is when the distribution of this population is approximately normal, and the distribution of this population is approximately normal. So if the population distribution for both of them are approximately normal, then we don't care about the size of N1 and N2, even if it's small, since we are getting this sample, both the samples from a normal population, then we don't care about the size of N1. Even if it is small, still the distribution of x bar 1 minus x bar 2 will be approximately normal. Therefore, now we know the sampling distribution of x bar 1 minus x bar 2. And we know its mean, we know its standard deviation. So how do we use this guy to estimate mu1 minus mu2? When I say to estimate, make inference about this one. So we know there are two types of inferences. One is the hypothesis test, and the other one is confidence interval. And we are going to see how to make a hypothesis test for this and make a confidence interval for this population parameter. All right, now let's start with the hypothesis. So for the hypothesis, of course, always, as before, we have three possibilities. And here we are trying to see the difference between mu1 and mu2. So most of the time, we would like to check whether mu1 and mu2 are equal or not. Okay, or mu1 is greater than mu2, or mu1 is less than mu2, and so on and so forth. So they are equal. Mu1 equals to mu2 is the same as mu1 minus mu2 equals to 0. Well, we know this one from algebra, right? If we take this one to the left side, then we get this one. And similarly, mu1 greater than mu2 means mu1 minus mu2 is positive, greater than 0. Mu1 less than mu2 means mu1 minus mu2 is negative. Therefore, this is how we write the hypothesis, null hypothesis or alternative hypothesis. Okay, this is usually the format. We don't, these are not that common. The reason why we use this one is it helps us with the computation, with the calculation. Okay, it's kind of straightforward. But here we have mu1 on this side, mu2 on this side. We don't have any number. We don't have any hypothesized value. Remember when we make hypothesis about a single population, we will write mu equals to some mu naught. This is a hypothesized value. So on the right side, we would like to have a number, which is a hypothesized value. And similarly, here we have a hypothesized value. But on the left side, even though they are equivalent. Here we don't have number, and that makes difficult for making the calculations. All right, and the next is figure out the test statistic for this kind of tests. So when we have two independent samples, sample 1 and sample 2, what we already know is that one is the mean, as we mentioned earlier. The other one is the standard deviation of x bar 1 minus x bar 2, which is given by this one. And the third property is when n1 and n2 are large, or if the population distributions are approximately normal, then the sampling distribution of x bar 1 minus x bar 2 is approximately normal. Okay, it follows approximately normal distribution. Therefore, if we know this one, if we have this satisfied, then we can calculate, we can standardize this, because remember, for any normal distribution, we can standardize it. We can convert it to a standardized normal distribution with mean 0 and standard deviation 1. And that's by writing z equals to the statistic minus the parameter divided by the standard deviation of the statistic. So the statistic in this case is x bar 1 minus x bar 2, and its parameter, well, this is an estimator of this one, right? This is estimator of this one. Therefore, and the denominator is the standard deviation of x bar 1 minus x bar 2. So this z will follow approximately standard normal distribution, okay, as long as we have these conditions. But the question here is, here I used sigma 1 and sigma 2 square. But usually in reality, we don't know sigma 1 and sigma 2. They are unknown most of the time. So if they are unknown, what we do is we use the sample standard deviation or sample variance to estimate this too. So for sigma 1 square, we have S1 square, estimator of this, and estimator of sigma 2 square is S2 square. So instead of this one, I will use this one. So if we plug this in here, if we replace sigma by S, then we don't have a normal distribution anymore. It becomes a t distribution, okay? So the two sample t test for a difference in population mean is over. The conditions for this hypothesis test or for this kind of test is the samples are independent. So here we have two samples, and both of them, they have to be independent. And the second condition is each sample is random sample from a population of interest. Okay, each sample has to be random. Well, we have to select each individuals in both samples randomly from the respective population. And otherwise, we have to have a reason to believe that each sample is representative of the respective population. And the third condition is the large sample size condition. Both N1 and N2 should be greater than 30, greater or equal to 30. Okay, or both population distributions are approximately normal. So either one of this is good enough to use this test statistic. But if number 3, the large sample size condition is failed, and the approximately normal distribution condition is failed, then we cannot use this one anymore. Okay, if any of this fails, we cannot use this one. Now, if the 3 are met, then we have the test statistic t, which is given by this formula. Now, if you notice, this one is exactly the same with this one, with the difference being sigma 1 is replaced by S1, and sigma 2 is replaced by S2. Other than that, it's exactly the same. And this one follows a t distribution with degrees of freedom given by this complicated formula. So now it's not straightforward. For one sample t-test or for paired t-test, if you remember, the degrees of freedom was just n minus 1, right? It was n minus 1. But now it's more complicated. So the degrees of freedom is given by v1 plus v2 squared. So this is basically s1 squared over n1 plus s2 squared over n2, the whole square over s1 squared over n1 over n1 minus 1 plus s2 squared over n2 over n2 minus 1. Yes, so this is, this is complicated. This is a bit, it takes time, of course, even to calculate it. But this is how we approximate the degrees of freedom, because now we are combining two samples and we don't, it's not straightforward. It's given by this formula, okay? Now, if we use this formula, n minus 1 is always an integer in this case, okay? The degrees of freedom has to be an integer. But here, if we use this formula, well, there is no guarantee that we get an integer. So what we do is we truncate it, we round it down, okay? So for example, if we have 15.0.67, for example, then the degrees of freedom becomes 15, okay? We round it down, not up. Remember, for n, when we calculate n using the margin of error, if we get n equals to 20.04, for example, we round it up, we make it 21. So in this case, we were round it up, but here we round it down. Okay. And well, the hypothesis for the alternative hypothesis, the three possible alternative hypotheses are given by this, and these are, of course, the same with the other tests that we learned before. And finding the p-value, of course, depends on the alternative hypothesis. So based on your, depending on your alternative hypothesis, which alternative hypothesis you are using, then the p-value will be the area under the curve to the left, to the right, or at the two ends, depending on which alternative hypothesis you are dealing with. All right, so let's look at this example now. So here, researchers, they wanted to answer the question whether mean college GPA for students who use Facebook is less than the mean college GPA for students who don't. So we have two groups. One is students who use Facebook, and the other one is students who don't use Facebook. And the two samples, we have N1, 141, who use Facebook, and 68, those who don't use Facebook. And the summary is given here in this table. And here we have, it says the two samples are representative to the two populations. So we have this granted. I mean, we are told that it's a representative. They select the students in a way that they represent the two groups. And as you can see, N1 and N2 are both greater than 30. Here we have mu1 represents the mean college GPA for students who use Facebook, and mu2 mean college GPA for students who do not use Facebook. N1 is 141, and x bar 1 is given by this, and the standard deviation of 1 this is 1, and this is 2, are these values. So we want to compare these two groups. We wanted to see if the first group has lower GPA than the second group. Now we need to translate this one into a hypothesis. So when we perform a hypothesis test, the first step is writing your hypothesis. Now, if we translate the problem into a hypothesis test, then what we have is that the null hypothesis will be mu1 minus mu2 equals to 0. And the alternative hypothesis will be mu1 minus mu2 less than 0. So mu1 is the mean of those who use Facebook, and mu2 is the mean GPA for those who do not use Facebook. Therefore, we are saying mu1, this is the same with mu1 less than mu2. Facebook users have lower GPA than those who don't use Facebook. That's what we are trying to see. And the method here, the potential method, of course, is a t-test statistic, because we have two independent samples. So here we have to be careful, because here, of course, we have two groups, and in the paired t-sample test, again, we have two groups. Even in this case, we have two groups. Let's call them X and Y. The difference is, in this case, the two groups are paired. Okay, they are paired in some way, in some meaningful way. But here, the two groups are independent. That's the difference. So always to figure out whether to use paired t-test or t-test for two independent samples, you have to see whether the two samples are independent or not. And that's one of the conditions here. The first condition is this one. This is the reason. The reason why we need to know whether the two samples are independent or not is to figure out whether to use paired sample t-test or this t-test. All right. So assuming they are independent, then our potential method is given by this t-test statistic. And when the null hypothesis is true, this test statistic follows a t-distribution with this, again, this complicated formula with this degrees of freedom. Okay. So one thing for your homework, when you work on your homeworks, what you could do is you can use the SALT, the technology, to find this degrees of freedom. I'm going to show you in a bit, but first let's proceed with this one. All right, so here we are going to use alpha 0.05. And the condition to check are, one is the independence, and the other one is the representative. The two samples, they have to be representative, and that one we were told that they are representative. And the independence is because we have one group of Facebook users, okay, and the other one is non-Facebook users. And we picked a group of students from each of them. So is there a reason to believe that these two are independent? Well, definitely, because these are totally different group of people, group of students, okay? So since our samples are from two different sample group, we can assume that, or there is enough reason to assume that they are independent. And the sample size criteria is met. Both of them, they are greater or equal to 30. Therefore, we can assume that the x bar 1 minus x bar 2 has approximately normal distribution. So we can use this t-test statistic. Now going to the next step is calculating the test statistic. So here we have the summary, n1, n2, x bar 1, x bar 2, s1, s2. And the test statistic is given by t equals to this formula. And if you compute this, you get this value. And the degrees of freedom, well, just to minimize error, it's a good idea to calculate this one by one. So here we have V1, which is given by this. So here, it's always a good idea to have a bit more digits on the after the point, because if you round this one to, for example, 2 digits, then you will get 0.01, which is when they are combined, like all the rounding errors, they become bigger and bigger, because if you start rounding at this early stage, and if you do the same thing with the other V, with this one, and so on, and then you are going to round some way in the calculation, let's say somewhere in here, and then at the end, the rounding error makes the answer, makes it far from the actual answer. All right, and the degrees of freedom is given by this formula. So substituting all the values, we get 205.181, and we round this one down, so the degrees of freedom is 205. This is the truncated degrees of freedom. And well, using this degrees of freedom for to find p-value, we only need, for t-distribution, we only need the degrees of freedom. Therefore, and the alternative hypothesis was mu1 minus mu2 less than 0. This is what we need, the less than sign. And therefore, the p-value has to be the area under the t-curve below or to the left of negative 8.09. And well, the value is approximately 0. Okay. Therefore, the p-value is 0. Here we have it. And because the p-value is less than the selected significance level, you reject the null hypothesis. So we reject the null hypothesis, and this is the decision. And the conclusion is, based on the sample data, there is convincing evidence that the mean college GPA for students at university who use Facebook is less than the mean college GPA for students at university who do not use Facebook. So this is based on this data. This would be your conclusion. All right. And well, there is so-called pool t-test. I'm not gonna give you any example about this one, because I will just give you what it means by pool t-test. Other than that, everything is the same with the previous one. But before we go to this one, let me show you this salt. So in your homework, you will get this link. I mean, it's in some of the questions they will give you, or the link to this one will appear in some of the questions. If not, you can just go to this webassign.net and you can find the salt. And here you go to inferential statistics, and here you choose which one you wanted which method you are dealing with. So you have one sample t, one sample proportion, two sample t, two sample proportion, parity, and so on. In this case, our test is the two sample t. Therefore, here it's asking us the information about the sample, the first sample, and then here we have the information for the second sample. So for the first sample, the mean is what is it? It's 3.06, and the standard deviation is 0.95, and this is 141. And for sample 2, it's 3.82, 0.41, and this is 68. So these are the information. And the next is the hypothesis test. Even you could test a confidence interval. If it's a confidence interval, then you choose this one, okay? Because we haven't seen it yet, but you can perform both of them, either hypothesis test or confidence interval. In this case, it's a hypothesis test. And what is your alternative hypothesis? You choose it here. So it's a less than. And this is the difference. It's not always zero, because here it was zero, of course. What is it? This is zero, but sometimes this may not be zero, okay, depending on the question. Therefore, this will be your hypothesizer value. All right. Now we have less than. I'm not going to change this zero, so generate results. And here we have. This is the hypothesis. This is the numerator. The test statistic is this one, and we got the same value. And the p-value, you see, is very, very small, almost zero. And this is the degrees of freedom. And the truncated becomes 205. And well, based on this one, then we take the decision. This is what we need from this result. Okay. All right. So going back to pool t-test. Now this pool t-test is when we have the reason to believe that sigma 1 square and sigma 2 square are the same. So suppose, well, we still don't know sigma 1 and sigma 2. We don't know both of them. They are both unknown, but we have a reason, maybe from prior study, from like a previous study, or anything. If we have a reason to believe that sigma 1 square and sigma 2 square are the same, then we can calculate a common estimator to both of them, because if they are equal, I need one estimator. I don't need S1 and S2 square, right? We don't need S1 square and S2 square, because we are saying they are the same. Sigma 1 and sigma 2 are the same. But these two numbers, they may not be the same, because we are calculating them from the sample data. Therefore, what we do is we find a common estimator to sigma 1 square and sigma 2 square. And that's what we call this S square pool. So this pool is n1 times s1 square plus s2 times n2 times s2 square over n1 plus n2. This is what we call the pooled so this has to be our book. They didn't include this one. This has -1. Yeah, it has -1. Sorry. All right. Then using this pool, S pool, replacing on the formula that we had earlier, the test statistic becomes x bar 1 minus x bar 2 minus mu1 minus mu2 over. Now, well, you may ask, how do we get this one? On the denominator, what we had on the formula was sigma 1 squared over n1 plus sigma 2 squared over n2. This was what we had earlier, right? Well, sorry, let me change it to S. This is S. Now replacing S1 and S2 by SP. SP is S pooled. So I will write this one SP square over N1 plus SP square over N2. And this is, you can factor out SP squared, and you will have N1 plus 1N2. And now you can take this one out of the square root because it's square. So we have S sub P 1 over N1 plus 1 over N2. And this is what we have here, okay? So that will be the test statistic. Everything else is the same. So we just replace this S1 and S2 by this SP, and then the formula becomes this one. Okay. All right, and the next inferential method is the constructing confidence interval. So, well, we already studied the sampling distribution of x bar 1 minus x bar 2, and we know the conditions that we need to check. The first one is the independence. Both samples, they have to be independent of each other. And sample 1 and sample 2, they should be representative to their respective population, or each of them, they have to be random samples. And the third one is we need a large sample size for both samples, or both populations are should be approximately normal. And once we have this one, then the confidence interval for mu1 minus, so this confidence interval is for this guy. This is what we are trying to estimate, okay? And the confidence interval for this one is x bar 1 minus x bar 2 plus or minus t critical value times this standard error, okay? And the degrees of freedom for this one is given by this, and we use this one to find the t critical value. Okay. Now, let's look at this example. So this report states that teenage girls who own cell phones send more text messages than teenage boys who own cell phones. So it's comparison of teenage girls and teenage boys who sends more text messages. And okay, where is the data? Okay. So the report states that the mean number of text messages sent per day for the sample of girls was 79. This is the mean. And the mean number of for the sample of boys was 56. So we have x bar 2 and x bar 1. The report also states that a total of 929 teens were surveyed and indicate that 51% of percent were girls. So we need to find 51% of this one. Okay. Okay. So just to make it easy, we have already the data here, but just to give you an idea how we find, here we have the x bar 1 and x bar 2 and s1 and s2, and n1 and n2. In total, we have 929. So 51% of this one is just multiply this by 0.51, and approximately you will get 474. Okay, and then the other one becomes 455. Just subtract it from this one. Okay, so here we have this, and using this one, we are asked to construct a confidence interval. So the method is constructing a 90% confidence interval. We have this, and here we need to define what mu1 is and what mu2 is. Always this is, it's not like because you may define mu1 to be the mean number of texts of sent by girls, teenage girls, or you may say mu1 is mean text, number of texts sent by teenage boys. Okay. Either way, it doesn't matter. It doesn't matter. I mean, it's up to your definition. So always you have to define which one is mu1 and which one is mu2. Okay, and based on that, you make your inference. And the conditions here, well, the large sample condition, it's met, and well, since we have two groups, group of teenage boys and teenage girls, then there is we believe that they are independent. Okay, so the first condition is also met. and we're gonna assume that this group are representative to their, what does it say, random sample? Well, yeah. So yeah, it's mentioned here. It says representative sample. So all the conditions are met. Therefore, we are good to go with the formula, with the inference. And to calculate the degrees of freedom, we use the same formula. And we get 1240. So using this t, we get the confidence the critical value, and the critical value is the same with the z critical value because this degrees of freedom is very large. Okay, therefore we use this critical value, and using this formula, we get the confidence interval is 22.024 to 23.978. So this is the difference, the confidence interval of the difference, mu1 minus mu2. So mu1 is the number of texts, average number of texts sent by teenage girls, and mu2 is the average number of texts sent by teenage boys. And the difference is somewhere between these two values. Therefore, the average number of texts sent by girls is more than that of teenage boys by a number somewhere in between this one. So they send texts higher than that the teenage boys by about 22 to 23 text messages. And the formally to interpret this one, we can say you can be 90% confident that the actual difference in mean number of text messages sent per day is between these two numbers. And since both endpoints are positive, you estimate that the mean number of text messages sent per day by girls is greater than the mean number of text messages sent by boys by somewhere between these values. Okay. So these are the two ways, or the two types of inferences. And for this example, again, let's use this, and we will change both of them. Here mean is 79, and the standard deviation is, I guess, 10. 474, 56, standard deviation 8, 455. Right. So, and here instead of hypothesis test, I will choose confidence interval, and I will change this one to 90% confidence interval. Okay. Do we assume equal variance? Well, not really, because we don't have any reason to believe that the variance of teenage boys and teenage girls are the same. So we will not check this one. But if you check this one, then the software or it will automatically calculate the pooled variance because they are the same. Okay. Now, when we compute the results, this is what we get. And well, 474, 455. Okay. There must be some error either in this calculation or, yeah. But as you can see here, it's 1240, and here it's 898. Well, it doesn't make much difference in the result, it doesn't make any difference, because as you can see, the degrees, the limits are almost the same, 22.023 and 23.97. And here, 22.024, 23, well, 24 still, and 23.976, 23.976. So the results are exactly the same, but the degrees of freedom, they are a bit different. I believe this could be kind of rounding error here, but the final result, the conclusion is exactly the same. And how about if we assume equal variance? You see there is difference. It increases, and there is slight difference here. Okay, if you notice this one, there is slight difference. And here the standard error is 0.59, and without this one, well, still is the same actually. There is a mild difference. But anyway, this is how we use the SALT software or technology to perform a hypothesis test, or to make a hypothesis test, or to construct a confidence interval. All right, so this is all for this lecture, and I hope I'll see you in the next lecture.